Hello, this is Richard Hammack's Calculus 1 course. We're in Part 5 of the course on integration. This is Lecture 45b, Substitution in Definite Integrals. This is a continuation of Lecture 45a, in which we introduced the substitution rule for indefinite integrals. Our plan for today is to, first of all, review what we did in Lecture 45a, Substitution for Indefinite Integrals. We'll look at some more examples, but then we'll switch over to applying the substitution rule to definite integrals. To begin with, let me remind you of what we talked about last time. I'm going to give you a quick review and setup of the substitution rule. It's really rather simple, and it's the chain rule in reverse. Suppose you have a function big F of x, and big F of x prime is equal to a function little f of x. So that would mean that big F is an antiderivative of little f of x. The chain rule would say that d dx of big F of g of x is big F of g of x times g prime of x. That's just the chain rule for differentiation. And you know that every time we have a differentiation formula, that gives us an anti-differentiation formula. This differentiation formula would tell us that big F of g of x is an antiderivative of f of g of x times g prime of x. So we get this anti-differentiation formula, or integration formula, that's the reverse chain rule. The integral of f of g of x, g prime of x dx, equals big F of g of x plus a constant c. Now in substitution, what you're going to do is, in this equation, every time you see a g of x that's inside the little f and inside the big F here, you're going to simplify things by just making that equal to a variable u. And if you do that, then the derivative du dx is g prime of x, and cross-multiplying by dx gives you du equals g prime of x dx. And when you make the substitutions that are given in the boxes here, in this reverse chain rule, you replace each g of x with u, and the g prime dx, g prime of x dx, you replace that with du. You get a simple integration formula. The integral of f of u du equals big F of u plus c, when you make those substitutions. Now, if you look at this, the left-hand side and the right-hand side on the top are equal because that's the reverse chain rule. On the bottom, the left and right sides are equal because big F is an antiderivative of little f. And furthermore, the two right-hand sides, those are equal because you've made the substitution u equals g of x here, and under that agreement, big F of g of x is equal to big F of u. So looking at those three equalities, this equals this equals this equals this, tells you that, sure enough, the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. And the equality that's in blue here, that's what we call the substitution rule. If u is equal to g of x, then the integral of f of g of x times g prime of x dx equals the integral of f of u du. And this has the effect of taking a very complicated integral, perhaps, it looks like this, that maybe doesn't match any integration formula that we know, and turning it into a simple integral, ideally one for which we have a formula for. So we're going to start off with some examples. We looked at a bunch of examples last time, but here are some more. To begin with, I'm going to do two examples that are intentionally easy, and you can actually do these examples in your head, but nonetheless, we're going to do substitution for them. Let's see. The first one is the integral of cosine of 2x dx. Now, we can do that in our heads because, let's see, it's cosine 2x. It's so much like integral of cosine x that you would expect that this answer should be, let's see, antiderivative of cosine is sine. So it should be sine of 2x, you'd think. But then the derivative of sine of 2x is sine of 2x times 2. I'm sorry, cosine of 2x times 2. And that doesn't match what you have here. It's cosine of 2x. And you then correct by multiplying by 1/2. So you'd get the answer to be 1/2 sine of x plus c, sine of 2x plus c. And so you can pretty much figure that out in your head just by kind of trial and error. But I want to do this with substitution. With substitution, you would say, well, this formula looks a lot like the integral of cosine of u du, where u is what's inside the, the u would be the 2x that's inside the cosine in the integral. And if u is equal to 2x, then du dx is equal to 2. So du equals 2 times dx. But over here, we just have a dx, not a 2 times dx. So we're going to multiply both sides of this by 2, by 1/2. And we get 1/2 du equals dx. So we can make the substitution 2x equals u, and dx equals 1/2 du in this integral. And we get the integral of cosine of u times 1/2 du. Pull out that constant 1/2. It's times the integral of cosine of u du. And that's a familiar integration formula. The integral of cosine u du is sine of u. So we get 1/2 sine of u plus c. And then replace that u with what it's equal to, the 2x. And our answer is 1/2 sine of 2x plus c. Now, that's exactly the answer that we sort of reasoned out in our head at the beginning. But of course, it does follow from substitution also, as we did here. Moving on to another example, how about the integral of e to the minus x dx? And this is also one that you should be able to do in your head. Maybe if you can't do it in your head now, you're going to quickly reach the point where you just do it automatically in your head because it's so simple. You're looking for an antiderivative of e to the minus x, and you're going to be thinking, well, that would just be e to the minus x. But then if you check that, the derivative of e to the minus x is e to the minus x times minus 1 by the chain rule. So it's minus e to the minus x, which is not quite e to the minus x. So you'd correct that in your head by saying, oh, the answer is going to be negative e to the minus x. And sure enough, if you take the derivative of minus e to the minus x, you get your e to the minus x back. So that would be the correct answer. But knowing that the correct answer is going to be minus e to the minus x plus c, let's go ahead and do this by substitution, the full-blown way. So this integral looks like the integral of e to the u du, where u is equal to minus x. So du dx would be equal to minus 1. And multiplying both sides by dx, or minus dx, we get minus du equals dx. So in this formula here, in this expression, the minus x is equal to u, and the dx is equal to minus du. And making those substitutions, this integral becomes the integral of e to the u times minus 1 du, which is minus e to the u du. And that's a familiar integration formula. So we get minus e to the u plus a constant. And that u is equal to minus x. So there it is, minus e to the power of minus x plus c. And that's exactly what we reasoned out in our heads. So as you're working lots and lots of these examples, pay attention to these real simple ones that you can do in your head. And as you work these, you'll develop a facility for bypassing the actual substitution rule in really simple situations like these. Let's continue with some other examples, just as a warm-up. Example 3, we've got the integral of 3 over square root of 5x minus 1 dx. And to analyze what's going on in here, let's just first of all simplify that by factoring out that constant of 3 and looking at this and think about, does it have any kind of simple structure? Well, it looks a lot like the integral of 1 over the square root of u du, doesn't it? If you let u be equal to 5x minus 1. So let's try that substitution and see if this gets simpler. If u is 5x minus 1, then its derivative is 5. So du is 5 dx. Now, up in this integral that we're leaving hanging for the moment here, you've got a dx, and you want to figure out what that dx could be replaced with. To see, you would isolate the dx that you have here. You could multiply both sides of this by 1/5, and you see now that dx is actually equal to 1/5 du. And that tells us that this dx can be replaced by 1/5 du. And this 5x minus 1, that's replaced by u. So making those substitutions, this integral becomes 3 integral of 1 over root u times 1/5 du. And let's take that constant of 1/5 to the outside. And the 1 over square root of u, let's write that as a power, u to the power of minus 1/2. And so we get this simple integral here that we recognize immediately as one that we could do with the power rule for integration. So carrying out that plan, we have our 3/5 coming down. And the integral of u to the power of minus 1/2 is going to be u to the power of minus 1/2 plus 1 divided by minus 1/2 plus 1. And then plus the ubiquitous c. Minus 1/2 plus 1 is positive 1/2, so we get this. 3/5 u to the 1/2 divided by 1/2 plus c. Simplifying that, reciprocating the 1/2 and multiplying by the 3/5, we get 6/5. Revert this u to the 1/2 to a radical, you get square root of u plus a c. And finally, remember that u is 5x minus 1. So now that substitution has done its job. We put back in the 5x minus 1. And we get an answer of 6/5 square root of 5x minus 1 plus c. Now, I'm not going to do it here, but you can always check your work. You could take the derivative of this. You'd probably use the generalized power rule to do that. And you will find that you do get your integrand when you do that. So it checks back. Here's another example. The integral of x times the cube root of the quantity x plus 9 dx. Now, when you're doing these problems, you usually want to think about converting radicals to powers, because we do, of course, have the power rule for integration that we like to exploit as often as we can. So maybe you write this as the integral of x times the quantity x plus 9 to the power of 1/3. And it looks like you could simplify this by making that x plus 9 be in u, so it's just u to the power of 1/3, and maybe you'd hope to use the power rule for integration there. So the idea is that maybe you can get this integral to look like the integral of u to the 1/3 dx. We'll put a question mark there because you never know until you do the substitution and see if you get a match. But this integral kind of looks like the integral of u to the 1/3 dx. So let's try that. And if we're aiming for that structure, then the u would have to be x plus 9. So u equals x plus 9. And then du dx would simply be 1. That's the derivative of x plus 9. So du is equal to dx. So that tells us that this dx right here, we can just replace that with du. And this x plus 9, we can replace that with u. And this looks great, except that then we still have this x over here that is just sitting there. What are we going to do with it? It needs to be turned into a u or some expression involving u somehow. We can't just erase it. That would be changing the problem. So what is x equal to in terms of u? Well, if you look at what's in the box here, we said u was equal to x plus 9. So that would mean that x is equal to u minus 9 when you scoot that 9 over to the other side. Let's put that down here. We also have x equals u minus 9. So we're doing this little extra step here that maybe we didn't do in the other substitution problems because we have to take care of this x. It needs to be replaced with something. We can't just leave it there and have this u to the 1/3. Then we have apples and oranges in here. It all has to be u's. So anyway, making the substitution, x plus 9 equals u, and x equals u minus 9, and this dx equals du. This becomes the integral of u minus 9, u to the 1/3 du. Now, notice at this point, we can multiply the u to the 1/3 into the parentheses. And let's see, here's what you get, the integral of u to the 1/3 minus 9, u to the 1/3 du. Now, this product here, u times u to the 1/3, that's u to the power of 1 times u to the power of 1/3. The exponents there would add, and we get u to the power of 4/3 minus our 9 u to the power of 1/3. So we're taking the integral of that. And notice we have two powers here, a difference of two powers. So we can use the power rule for integration twice there. So on the u to the 4/3, the integral of that is u to the 4/3 plus 1 divided by 4/3 plus 1. Then minus our constant of 9 times the power rule applied to u to the 1/3 would be u to the 1/3 plus 1 divided by u to the 1/3 plus 1, and then plus our c. And simplifying that, we get u to the 7/3 divided by 7/3 minus 9 u to the 4/3 divided by 4/3. Reciprocating the bottoms, multiplying times the tops, and converting these fractional powers back to radicals, we get 3/7 cube root of u to the 7th minus 27 over 4 cube root of u to the 4th plus a c. And finally, to get our answer, we change that u back to an x plus 9. So here's our answer. The integral that we were looking for was 3/7 cube root of x plus 9, whole thing to the power of 7, minus 27 over 4 cube root of x plus 9 to the power of 4 plus c. Now, we're not going to do it here, but you could check this by differentiating this. And you will, once you collect all like terms and so on, get your integrand that appears here. So again, with this problem, and as with all the substitution problems, we started with an integral that didn't match any integration rule that we knew. And we chose a substitution to make, and we converted that to a form which has integrals whose formulas we do know. Like here we could use the power rule for integration, where it wasn't clear how that could be used up here. So that's what we do in all of these problems. Okay, we're going to move on now to, we'll keep working with substitution, but we're going to look at substitution in definite integrals, not indefinite integrals. And I want to start out with some motivational problems, some warm-ups. Let's first of all think about the integral from 0 to 1 of u to the 5th du. Now, if you think about the fundamental theorem of calculus, what you'd be looking for in this one is an antiderivative of u to the 5th, and you'd evaluate from 0 to 1. So this problem really comes down to finding the antiderivative of u to the 5th, an integral of u to the 5th. And well, that's easy because we have the power rule for integration. And the antiderivative that we're looking for is u to the 6th over 6th. Oh, and then you plug in 1 to that and subtract off what you get when you plug in 0. You get 1/6 minus 0 over 6. And you get an answer of 1/6. Okay, well, there's no substitution there. Let's move on to a slightly different problem. How about the integral from 0 to 1 of x squared plus 1 to the 5th times 2x dx? Kind of like what we had before, but a little bit more complicated. But the basic strategy is the same. You'd use the fundamental theorem of calculus. You'd look for an antiderivative of x squared plus 1 to the 5th over 2x dx to put, times 2x to put right here. And then you'd evaluate from 0 to 1. So the only thing that makes this problem different from the one that was up here is that maybe we can't find that antiderivative as quickly as we could in this simpler problem. So what I propose that we do is just hold off right here and go down to a separate line and start looking for the antiderivative big F of x that we're going to put here and work that out as a separate computation. So this antiderivative big F of x should be the integral of x squared plus 1 to the 5th 2x dx. Should be the antiderivative of this integrand. And for this one, you'll recognize this integral as something that we could apply substitution to. You'd probably want to make a substitution of u equals x squared plus 1 to get this to look like u to the 5th. So if u is equal to x squared plus 1, du dx is 2x, and du is 2x dx. And this is one of those perfect match problems where the 2x dx, it happens to be right there, so that's equal to du. And of course, the x squared plus 1 is a u. So this integral becomes the integral of u to the 5th du. Power rule for integration converts that to u to the 6th over 6. And now plugging in the x squared plus 1 for the u gives us our antiderivative of x squared plus 1 to the power of 6 over 6. And now there should be a plus c, but remember, we're using the fundamental theorem of calculus, so any antiderivative is going to work here. So we don't need to add the plus c, just take plus c equals 0. And besides, we don't even have room to put the plus c here. So in summary, this x squared plus 1 to the power of 6 over 6, that's what goes right here. So we had left this line just hanging when we did this separate calculation, all to find out what goes here. So we put it there, and now we can continue on this line. You plug in your 1 to this and subtract off what you get when you plug in 0. So that's 1 squared plus 1 to the power of 6 over 6 minus 0 squared plus 1 to the power of 6 over 6. And let's see, this is 2 to the 6 over 6. 2 to the 6 is 64 minus 1 to the 6 over 6. So that's 63 over 6, or 21 over 2. So there's our answer. This definite integral equals 21 over 2. So with this problem, we had a definite integral. We used the fundamental theorem of calculus, but then we had to pause and do a whole separate computation to find that antiderivative. And in that computation, we used substitution. Then we continued along and we got our answer. Now, this is fine. You could do every definite integral problem that needs substitution this way by making a separate computation, but you'd quickly tire of that because I think you can see that you could probably save some steps here by just making the substitution in line with this definite integral rather than going off and doing a separate computation down here. So I want to do this exact same problem a different way where we do everything in line without going off to the separate computation. So exactly the same problem, the integral from 0 to 1, x squared plus 1 to the 5th, 2x dx. Now, it's the same problem. We know the answer is going to be 21 over 2. But pay careful attention to what happens here, because what we're going to do is come up with a new formula that comes out of the approach that we take for this one. There is one point where something sort of unexpected perhaps happens. So you want to be on your toes here. If we look at this definite integral, you would say, well, we want to make that look like the integral from 0 to 1 of u to the 5th du. It almost has that exact structure. So you might say, well, let's make a substitution where u is x squared plus 1, and then du dx would be 2x, so du is 2x dx. And that tells us, just like what happened over here, that this 2x dx is equal to du, and of course the x squared plus 1 is u. So making those substitutions, this integral becomes the integral of u to the 5th du. But I want to pay careful attention to these limits of integration, 0 and 1. In the problem that we started with, the variable is x, so x was going from 0 to 1. And then we made a substitution. We changed the variable. U is equal to x squared plus 1. And we got this integral here, and that was the integral of u to the 5th du. But I want to remind you that these limits of integration are x values, and they're not u values. So to emphasize that, I'm going to write x equals 0 and x equals 1. This is the integral from x equals 0 to x equals 1 of u to the 5th du. Now, we need to change those x values to u values to get the right answer. Look what would happen if you left this as just the integral from 0 to 1 of u to the 5th du. That would be this integral, and the answer is 1/6. And you know the correct answer for this different problem is supposed to be 21 over 2, not 1/6. So what are we going to do? Well, we're going to convert these x values to u values. Remember that u is equal to x squared plus 1. So up here we have x equals 1. If x is equal to 1, what is u? Well, then u would be 1 squared plus 1, or 2. So when x equals 1, u is equal to 2. So we're going to replace this upper limit of integration of x equals 1 with its u value of 2 in this integral where we have the variable u. Likewise, what happens when x is equal to 0 for this lower limit of integration? Well, if x is equal to 0, u, of course, is x squared plus 1, because that's the substitution we made. So u would be equal to 0 squared plus 1, and that's 1. So this x equals 0 gets converted to a 1. And it's implied here that it's u equals 1 because our variable here is u. All right, so we have the integral from 1 to 2, u to the 5th du. And now this is an easy one because this is just it's a power rule for integration problems. It's almost identical to what we did up here, except the limits of integration are different. So continuing with that approach that we did way up here, the answer is going to be let's see, our antiderivative is u to the 6 over 6, and we go from 1 to 2. So that would be 2 to the 6 over 6 minus 1 to the 6 over 6. And that works out to be 63 over 6, which simplifies to 21 over 2. So that's our answer. And you'll notice that it is exactly the answer that we got using this alternate approach. So what we're going to do is this. We tend to work definite integrals involving substitutions in line as we did here. And you can tell from comparing these two examples on the second and third on this page that keeping things in line actually involves a lot less writing and work than doing a separate antiderivative problem, as we did here. However, you have to be really careful to change your limits of integration from the original variable x to the new variable u. You have to make that conversion of those limits of integration using the choice of substitution that you made in the first step. Okay, so we're going to summarize this idea in a formula. I'm going to remind you, first of all, of the substitution rule for indefinite integrals, and then we're going to tie that up with extrapolating a new rule from that problem that we just saw a moment ago. The substitution rule for indefinite integrals says that the integral of f of g of x times g prime of x dx is the integral of f of u du, where u is equal to g of x. That's just the plain old substitution rule that we've been using all along. Now, here's the substitution rule for definite integrals. It's based on that example that we just did. It's really just like the regular substitution rule, except you have limits of integration. You've got the integral from a to b, f of g of x times g prime of x dx. Well, for definite integrals, it works just like what we had before. You get the integral of f of u du. But as in the example that we just worked, you have to change these x values of a and b to u values. And here you're making the substitution g of x equals u. U equals g of x. So this x value of a turns into a u value of g of a. The x value of b turns into a u value of g of b. That's the substitution rule for definite integrals. So let's work a few examples of that substitution rule for definite integrals. We'll start with this one, the integral from 1 to 2 of x plus 1 over x squared plus 2x whole thing squared dx. Let's simplify that by bringing that power of 2 on the bottom up as a negative power. So we get the integral from 1 to 2 x squared plus 2x to the power of minus 2 times x plus 1 dx. And let's think about our substitution. This integral looks a lot like a definite integral of u to the minus 2 du. And be a little unspecific about what those limits of integrations are. We're just looking at the structure of this. So if we're going to get this integral to look like this simple one, then u is going to have to be x squared plus 2x. So we make that substitution. U equals x squared plus 2x. Our du dx would be 2x plus 2. That's the derivative of x squared plus 2x. And so du is 2x plus 2 dx. But up here, we don't have a 2x plus 2 dx. We have an x plus 1 dx. Well, we could get an exact match to that by multiplying both sides of this expression for du by 1/2. So 1/2 du is x plus 1 dx. So now up here in this definite integral, the x squared plus 2x is u, and the x plus 1 dx is 1/2 du. So we'll make that substitution. So there we go. The x plus 1 dx is the 1/2 du, and this up here is the u to the minus 2. But remember, these limits of integration, which in this line are x values, have to be converted to their corresponding u values. So keep it in mind over here that u is equal to x squared plus 2x. When x is equal to 2, u has to be 2 squared plus 2 times 2. And when x is equal to 1, u would be 1 squared plus 2 times 1. 1 squared plus 2 times 1. So then we factor out the 1/2. 1 squared plus 2 times 1 is 3. 2 squared plus 2 times 2 is 8. So now we've got this integral, 1/2 integral from 3 to 8, u to the minus 2 du. And we can now use the fundamental theorem of calculus here with the power rule for integration. So just keep that 1/2 on the outside. And the antiderivative u to the power of negative 2 would be u to the power of minus 2 plus 1. That's u to the power of minus 1 divided by minus 2 plus 1 from 3 to 8. And let's bring that negative power down to the bottom. We get, in the box here, we get negative 1 over u from 3 to 8, whole thing times 1/2. That gives us 1/2 at negative 1 over 8 minus negative 1 over 3. And following that through, let's see, we need a common denominator here in this difference. Looks like the common denominator will be 24, so we'll multiply this fraction by 3 over 3 to get minus 3 over 24. This one we have to multiply by 8 over 8 to get minus 8 over 24, but then combining that minus with this one, you get plus 8 over 24. And adding up those fractions, you get 5 over 48. So this definite integral equals the number 5 over 48. So much like our old integration by substitution problems, the only difference is here you have limits of integration that you have to convert to u values once you make your substitution. Let's look at another example. Integral from 0 to ln of 5 e to the x times 3 minus 4 e to the x dx. By now you probably know to sort of scoot that e to the x over to near the dx. I'm going to do that because here you're hoping to get e to the x dx equaling to a du with some kind of substitution. Let's see. Well, there are actually a couple of ways we could go about this one. And one of them would be to multiply this e to the x into the parentheses to get 3 times e to the x here, and we can find an antiderivative of that. And then we have minus 4 times e to the x squared, which would be minus 4 times e to the 2x, and we could find an antiderivative of that. So that's one possibility that would lead you to a correct answer. And that would bypass substitution, actually. But I'm going to try substitution in this one. And if you look at this, it looks like a definite integral of this quantity right here is just a plain old u. No power, just plain old u. So we could try to make this look like a definite integral of u du. And if we did that, then u would have to be 3 minus 4 e to the x. And then what's our du dx? It would be minus 4 times e to the x. So du would be minus 4 e to the x dx. And notice we have an e to the x dx here. We could isolate the e to the x dx in this equation by multiplying both sides by negative 1/4. So we get e to the x dx equals minus 1/4 du. So that tells us way up here in this problem that this 3 minus 4 e to the x could get replaced by a u, and the e to the x dx by a negative 1/4 du. So making that replacement, this got replaced with u, e to the x dx got replaced with minus 1/4 du. So we converted from x to u in this line. So these x limits of integration up here, they have to be changed to u limits of integration. And remember that u is equal to 3 minus 4 e to the x. So when x is 0, that's 3 minus 4 e to the 0. When x is ln of 5, that's 3 minus 4 e to the power of ln of 5. So let's simplify that. Bring out that negative 1/4. And let's see. Up here, e to the ln 5 is 5. So this is 3 minus 4 times 5. That's minus 17. And here, e to the 0, remember, is 1. So that's 3 minus 4 times 1, which is minus 1. So we get negative 1/4 integral from minus 1 to minus 17 u du. And an antiderivative of u is u squared over 2. So applying the fundamental theorem of calculus gives us negative 1/4 u squared over 2 from minus 1 to minus 17. Plugging those numbers in and turning the crank gives us an answer of minus 36. So there we go. And you may also want to try in your free time this, the alternate approach by multiplying the e to the x into the parentheses here and integrating term by term. You'll get the same answer that we got here. With a lot of these problems, there will be multiple approaches. Okay, here's another one. Integral from 3 to 5, 1 over 3x minus 4 dx. So this one looks like a definite integral of 1 over u du, where u would be equal to 3x minus 4. So let's try that. U is 3x minus 4. So then du dx would simply be 3. Du would be 3 times dx. But up here, we don't have a 3 times dx. We have just a dx. So we're going to multiply both sides by 1/3 to get dx equals 1/3 du. So we're going to make those substitutions here. This dx is going to turn into 1/3 du, and the 3x minus 4, that's going to turn into a u. So there we go. 1 over 3x minus 4 turned into a 1 over u. Dx turned into a 1 over 3 du. But in going from the variable x to the variable u in this line, we have to convert our x limits of integration to u limits of integration using the conversion formula u equals 3x minus 4. So up here, when x is 5, u is going to be 3 times 5 minus 4. And down here, when x is 3, u is going to be 3 times 3 minus 4. So pulling out the 1/3 and doing the arithmetic in these limits of integration gives us 1/3 integral from 5 to 11, 1 over u du. Now this is an easy integration problem. Here, finally, we can just use the fundamental theorem of calculus there. The integral of 1 over u is ln absolute value of u. And we evaluate from 5 to 11. So 1/3 ln 11 minus ln of 5. And that would be a perfectly sufficient answer. But you'll notice that ln of 11 minus ln of 5, you could use a ln property there, a log property, to convert those to ln of 11 over 5. So I'm going to write the final answer here as 1/3 ln of 11 over 5. New example, integral from pi squared over 4 to pi squared of sine square root of x divided by square root of x dx. So this one, let's see, let's sort it out just for sort of aesthetic reasons to analyze what's going on. Let's break this fraction up into two separate fractions and think about this. You've got a sine square root of x here, so you might say that this looks like a definite integral involving sine of u, like sine of u du. So let's try that. And as always, when you make these substitutions, sometimes you don't know at the beginning whether or not they're going to work. But let's try this one. This looks like the integral of sine of u du. So taking that approach would mean that u has to be equal to the square root of x. And computing the derivative of that, du dx is 1 over 2 square root of x. So du would be 1 over 2 square root of x dx, if you multiply both sides by dx. And let's see, that's very close to what we have over here, 1 over root x dx, except it's got this 2 here. So no problem, we can multiply both sides of this equation by 2 to get 2 du equals 1 over root x dx. And now that 1 over root x dx is a perfect match to what we have here. So we could replace the 1 over root x dx with du now, or 2 du now. So applying these two boxed equations to what we have here, the sine squared of x turns into sine of u, and the 1 over square root of x dx turns into 2 du. And so we passed from an x variable to a u variable, so we also have to change these x limits of integration to u limits of integration. And remember, u is just the square root of x. So when x is pi squared, u has to be square root of pi squared. And when x is pi squared over 4, u is going to be a square root of pi squared over 4. So factoring out the 2 and doing those square roots and the limits of integration gives us 2 integral from pi over 2 to pi sine of u du. And now we're in a very fortunate position of having a simple definite integral here, one that you could have done back in section 4.9. So applying the fundamental theorem of calculus, we get 2 minus cosine of u from pi over 2 to pi. Minus cosine being an antiderivative of sine, after all. Plugging those values in and turning the crank, we get this. Let's see, cosine pi is 1. Cosine pi over 2 is 0. So 2 times minus 1 minus 0. And that gives us an answer of 2. That's it for today. And we have only one more lecture in this course. Lecture 46 coming up will wrap up the whole course. I'll see you then, and goodbye.